chloride? Carbon chloride. Do we go with that? Carbon tetrachloride. They're both what?
Non-metals.
Non-metal. So carbon tetrachloride. Now I'm going to assume we did not do this one together, I don't believe. But I'm going to assume that you could have gotten to the Lewis dot structure with this. I would take a look at it, and I'd say, okay, carbon's not going to violate the octet rule because I've got those 4 rules tucked away really well. Now, tell me why. Because in Rule 4, it mentions the halogens, the heavier halogens, it mentions chlorine. Why don't we worry about chlorine violating the octet rule? It's not the central atom. You do not worry about it if it's not the central atom. All of the violators, except hydrogen, are always central atoms, and hydrogen is never a central atom because it can only have 1 bond. Okay, so you got to there. Now let's cut out across here. We want to count atoms here. Charles, how many atoms do you see around the central? 4. Allison, how many lone pairs on the central? 0. Antonio, how many things? 4. And the new shape, the new orientation is tetrahedron. Okay, now just a vocabulary thing. You also hear tetrahedral used interchangeably. Tetrahedron is the noun. If you say or hear tetrahedral, it's the adjective, and they really should say tetrahedral arrangement. But either one, you know you're talking about the same thing. If you build it, here's what it looks like, and I want you to build one. You got to pick the right jack to do this, the right connector, and it is the silver colored one. Okay, here's where my cat story falls down. Because if I were doing a cat story, if a cat cannot fly or hover in space, in the cat story, you would have one here, one here, one here, and one directly behind me. Bad news, because what is that angle again? Square planar would be bad news, because it'd be what? What's the angle? No. Square planar, like this. What's 90. Bad news. Okay, so for the first time, we got to go into 3-dimensional space. You have 4 things around your central atom. Now, so let's see if you can build it. Okay, I'm seeing some good ones. Use your silver joint because not all of these will work. Okay, great. Everyone I see is great. So what we're talking about is carbon in the middle, chlorine, 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 chlorine. Now watch carefully. I always try to hold this in the same orientation. I've got one up and a tripod down. But now watch. In reality, there's no unique up spot because watch what I can do. Here's the up. I still have a tripod down. Now this challenges my artistic talent. But here's my generic tetrahedron. And it's a tiny bit different than what's in the book. I'm going to put carbon here, chlorine, 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 chlorine. This would be my best first sketch, but let me interpret it for you. If it's a solid line on the board, it means it's in the plane of the board. A wedge is coming out towards you. A dotted line is going back behind the plane of the board. Now in your book, they do a reverse wedge, and I think that's real confusing. This is bad enough. So if it's going back behind, it's going to be a dotted line. So that's what I'm trying to draw. I hope you have more artistic talent than I. Generally what happens, because I tell students they may bring these, make your own and bring them on the test day. You can't share them, but you can have your own little set. Now, wouldn't buy them, make your own. You know, toothpicks, gumdrops, whatever. Be creative. Styrofoam and toothpicks would also work. Okay, because if you visualize this, it's going to help a whole lot. Now, this is our tetrahedron. it's so much better because the bond angle here, this is probably one you don't know unless you've read ahead in the book. It's 109.5. Now, how do I know that? I've been working with these things so many years, it's in my head just like 180 and 120 is. But it's probably not in your head yet, because you don't see this in everyday life. So, for our angle, 109.5 degrees, and since we have no lone pairs, these two are the same. You might want to make a note, these to yourself. Same if no lone pairs on central atom, because I've had 2 or 3 questions about that this morning. And we're going to have time this morning to do some that have lone pairs on the central atom. Now, why are we using 3-dimensional space? Because if you had this, and I saw 1 or 2 of you hold this up first, bond angles are 90. Bad news. Your mother-in-law is on the same block. Too much crowding. So we go to 3-dimensional space and we break that 100-degree barrier, and it's 109.5. And that's from here to the center to out. All of them are identical. Okay, now let's talk polarity. Okay, I got a carbon, I have a chlorine. Who's more electronegative? Chlorine. Okay, so is this bond polar?
Yes.
Yes. Force, 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 force. Okay, if you've had a physics class or a math class where you've added vectors, listen. If you haven't, just sit there acting like you're listening. Okay, if I took these 3, force, force, force. You know, a vector is a force that's directional. If I added those 3 together, I would get a resultant that is straight down and would be equal and opposite to the top one. Okay? Or you can look at the symmetry and say, if you've got forces like that, would it cancel? And if you don't see it, accept it on faith. Yes, it will cancel. So, we're going to say this is non-polar. What if I changed one little thing? I put on a hydrogen. Okay, hydrogen and carbon have almost identical electronegativities. In fact, we say essentially, and this is something new, a CH bond is essentially non-polar. It's so much like being twins. Okay, they were born 9 months apart. So same size, same age, whatever, or almost the same age. Okay, so almost no force here, but force, force, force. You would have to say this molecule is what? Polar. But all you have to do is switch to having 4 the same in a tetrahedron, and you are non-polar. So think what power you have. I could go CF4. I could go CH4 because a hydrogen, you know, in your book, in that periodic table, the hydrogen also belongs sometimes over in the 7A family. So the hydrogen can substitute for a halogen in these. Okay, I've got this, I've got this, I've got that, and then let me do something else to you. Look at these first. Non-polar, 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 and so forth. If you know this one, you should immediately see it's going to be the same bond angles, the whole business. Okay, now, this one's trickier for students generally. Instead of switching out for a family member for the guys out and around, I've switched out the central atom because carbon and silicon are in the same family. I look at that and go, hey, I know it's non-polar. If you have that one on the test or the review sheet and you labored through that and then you spot that, you should see the similarity. Now, there's no law you can't start from scratch each time, but it takes a lot more time than to say, hey, I know it's going to be similar. Okay, resonance on this guy. Aaron, resonance? 0. Good job. Now, let me tell you where we are in the book. Okay, section 8-5 is what they call an AB2 case and no lone pairs. They're calling A the central atom and B are the two atoms around it. So this would be your beryllium chloride case that we took last time. AB3 with no lone pairs. The boron trifluoride case that we just did. Here, 8-7, AB4 and no lone pairs. Carbon tetrachloride. Okay, now we're moving into the next section, and here's what the one we're going to do. I'm going to take ammonia. I'm going to assume, although we have not done it together, we did ammonium, we didn't do ammonia. You could get to here. We look at it, we go, nitrogen's our central atom, and we know nitrogen's never going to violate. And then hydrogen we know always violates by rule 1. It just needs 2. So you know what that means? Hydrogen will never have a multiple bond, okay? And hydrogen will never be a central atom. It's going to be on the edges. Okay, so here's our ammonia. Let's go through and see what we can answer about it. Okay, when we look at our number of atoms here, Timothy, how many atoms? 3. Marco, how many lone pairs?
1.
1. How many things, Nina?
3. Oh, 4.
4. Because lone pairs count. This is our first case where we've had a lone pair. So this is the total of those 2 things. Okay, so we have 4 things. Anytime you have 4 things, orientation is always the same. When you talk about orientation, it's an always, always, always thing. If you have 2 things, orientation is always what? You have 2 things. Orientation is always linear. You have 3 things, and I don't care what they are. Orientation is always what? Trigonal planar. You have 4 things. Orientation is always what? Tetrahedron. And I don't care if it's 4 atoms or 3 atoms and a lone pair like this case, which is what section 8-8 is. Our orientation is tetrahedron. Okay, we have a lone pair. That means these 2 columns are not going to be the same, and that's what's generated several questions before. I'm going to use a red. So what you need to do is have 3 of one color and 1 of a different color. Charles, yours is perfect. Okay? So don't have them all the same color. Have something to designate a lone pair. Okay? In the air. Okay. You're searing? Okay, good. Everybody's all right. Now, notice something here. I put my lone pair in the up position because I always try to hold it for you this way. Here's why. I want you to have it implanted in your brain, 1 up, tripod down. Just an aside. If you go on to organic chemistry, they are so weird. They take the tetrahedron and they hold it like this, so it's a V coming out this way and a V coming back that way, and I don't like it. They can do what they want. Okay, so I like to hold it 1 up, tripod down. Okay, now notice, I'm going to trade out this red with this black. Okay, now, it's in the tripod part, but all I got to do is rotate my molecule. In other words, if you have a lone pair in a tetrahedron, stick it where you want it. The answer is always going to be the same, but it'll be easier to visualize if you put it in the up spot. Okay, here's the new part. Okay, how do we really know what this shape is? We take it to a sophisticated laboratory, we zap it with X-ray. When X-rays hit something solid, like a nucleus, they bounce back if it's a direct hit. So we do with our instrument, we're zapping it with X-ray, we have X-ray film back here. So here comes the X-ray, it hits the nucleus, fires back. It's a nucleus, fires back. But the lone pairs, those X-rays just zip right through, like those lone pairs aren't even there. Okay, so when we talk about molecular shape, you want to take your special one off, because when you talk about a molecular shape, you say what you see when that one's gone. Now it's holding a spot, but we can't see it. So we call this a trigonal pyramid. Think about pyramids. There's all different kinds of pyramids. You have a pyramid with a triangular base. You can have a pyramid with a square base. You can have a pyramid with a rectangular base. Does everybody see this? Here's your point of your pyramid. Think Egypt. I don't know if they got triangular. Anybody been in Egypt? Do they have triangular bases in the pyramids, or they're square bases, aren't they? Okay. But we can have this kind. So a trigonal pyramid. So when we talk about molecular shape, I got to say trigonal pyramid. Okay? Now, you may see it as something different, but you got to see it the way the original guys saw it. So trigonal pyramid.
So that's only with lone pairs.
If you have a lone pair in this spot, you know, in this case,
Oh, yeah.
it's only in this case,
Okay.
one lone pair. Okay, if you have, let me just take it from the top. You have 4 things around the central atom, and one is a lone pair. Molecular shape, trigonal pyramid. Okay, now, bond angles we know in a perfect tetrahedron. How's your short-term memory? 109.5, good deal. Okay, if you have a lone pair up here, it does not have another nucleus to keep it under control. So that lone pair kind of balloons out, does a little bit of a squeeze play on these angles. Because that lone pair is very repulsive. It's like the new Tomcat just moved into town on the block. So this stuff is being squeezed because he wants more turf. And so what we say, angle is less than 109.5.
So it's like there's lone pairs,
All right, one lone pair.
only one.
Yeah. Now, in another textbook, and I don't think your textbook says this, how much of a squeeze is this? It's only about 2.5 degrees. It's not a big deal. Now, this does not stand for angle. It stands for less than. You need to know about the squeeze play. Okay, but what they have found is generally, as a ballpark figure, this squeeze play is about 2.5 degrees. So I would say, and you do not need to know this, but I just wanted you to see it's not a real huge squeeze. So 2.5 degrees off that gives me 107 degrees, and when they took this in and zapped it with X-ray, that's pretty darn close to what it really is.